Hi everybody, this is the second of what most likely will be 3 videos covering section 4 of chapter 4, combinations and permutations. In our first video, we talked permutations. In this video, we are going to talk combinations. So we've already done this, factorials, we've already done permutations, and we're going to do technology as we do combinations, just like we did in our previous video. Okay, so let's start off with permutations. And remember in our last video, we talked about or we introduced the idea with having 5 distinct objects and determining the number of ways or the number of permutations that we can have if we select only 2. And remember, when you see the word permutations, you're thinking that order matters. And as you can see, as we mentioned before, there happen to be 20. Well, in combinations, order doesn't matter. We're selecting objects from a group, and if we get a 1 and a 2, or a 2 followed by a 1, it doesn't matter. We'll consider that the same thing. So these two would be considered the exact same outcome. These two would be considered the exact same outcome, and so forth. As a matter of fact, this is what it will look like when order doesn't matter. Notice that we have, in total, we have 20 items, but every single item has 2 permutations. And so as a consequence, instead of having 20 items, we actually have 10. And how do we get that? Well, we get that from, first, our permutation formula, which is n factorial divided by n minus r factorial. And then noticing that every single every single group, one, has their very own has r factorial permutations. Notice here we are taking collections of 2, and for every collection of 2, there are 2 factorial ways that they can actually be ordered. As a consequence, the formula for taking r objects from n is the number of permutations we have, n minus n. I forgot the factorials there. Divided by the number of ways each of the objects or each of the collections subgroups can be permuted. So we have permutations and then the number of ways that these objects can be arranged. And that ends up being our formula for the number of combinations. And there it is. Suppose that we have n distinct objects. Suppose that we select r of them. Then the number, and suppose that the order does not matter. That's the important thing. Then the number of combinations that you can have, we're going to use the notation NCR, is actually the number of permutations divided by the way that each group of r can also be permuted by itself. So we have n factorial divided by r factorial times n minus r factorial. So that is the formulation for combinations. And notice also, once again, we have this cute little NCR that we can work with. Okay, so let's take a look at a couple of examples. And here is one. How many ways can Patricia choose 5 pizza toppings from a menu of 15 pizza toppings if each pizza topping can only be chosen once? So you need to read this and then discern that order does not matter. And if that's the case, then our answer is going to be 15C5, which will be 15 factorial divided by 15 minus 5 factorial times, that should be down there, times 5 factorial. Okay, so that will be 15 factorial divided by 10 factorial times 5 factorial. Or we can simplify that as 15 times 14 times 13 times 12 times 11 divided by 5 factorial, which is 120. And that will give us 3003. As you can see, that's a lot of work. There should be an easier way to do that, and there is. Here's our calculator. What we can do is type in 15, math, go over the probability, hit 3, here we have NCR, so go ahead and hit 3, and then put in your 5, and there we go, that is our answer, 3003. Get the exact same thing. Okay, here's our next problem. There are 24 people in office with 6 different phone lines. If all of the lines begin to ring at once, how many groups of 6 people can answer these lines? Once again, in this particular case, you need to read this and discern that order doesn't matter. It doesn't matter which one was the first one, doesn't matter which one was the second one, and so forth. Therefore, this is a combinations problem, 24C6. And that will be 24 factorial divided by 24 minus 6 factorial times 6 factorial. Okay, so that would be a little daunting to do by hand, but that's cool. That's why you got to make computer calculators, right? Here we go. So what we're going to do is type in 24, math over the probability, there we go. Go down to NCR, type in 6, and that is our answer, 134,596. Now, if you have one of those newfangled calculators, let me bring that newfangled calculator up. The way you'd want to do that is, instead of probably putting in the 24 first, just go into math, go over the probability, go down to NCR, put in 24 there, move the cursor to the next subscript, put in 6, there's your answer, the exact same thing. Okay, now it turns out that this is also known as the binomial coefficient. And why is that the case? Well, let me show you in a particular example. Notice here we have the binomial expansion of x plus a. We have x plus a raised to the, which is a binomial raised to the 4th power. And if you expanded it, you would get this. Okay? Well, it turns out we could also write that as the binomial coefficient of 4 0. Sometimes we call that 4 take 0, which by the way is 1, times x to the 4th. A binomial coefficient of 4 1, which is 4, x cubed a. That is a typo, that should be a 2. Sorry about that. 4 2, which will give us 6, x squared a squared. The binomial coefficient here, which once again is 4, and xa cubed, and then finally we're back to 1. So we call this the binomial coefficient because it provides the coefficients of a binomial expansion. It's actually a very convenient way to do that if you need to compute this. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. Stay tuned for my last video, which will be doing your homework. Until then, this is Bob Boyle, signing off.